All right, welcome back. Dr. P here, and in this lecture we'll take a look at diastereomers and meso compounds. Now, what is a diastereomer? A diastereomer is a type of isomer I'll say diastereomers are non-superimposable, non-mirror image stereoisomers. Now, I realized I haven't defined stereoisomers, after this lecture, the next lecture, I actually want to sort of summarize isomers in general, and I'll talk more about stereoisomers specifically, but stereoisomers have the same connectivity. So we saw with our enantiomers, we had the same four groups attached to a carbon that was chiral, and then just a different arrangement, whether it was R or S. Diastereomers are also stereoisomers. Like enantiomers, they are non-superimposable. However, they are not mirror image isomers. All right, so what's an example of a diastereomer? Well, we can have cis-trans isomers. So with alkenes or rings. In actuality, the rings will often involve or can involve chiral carbons as well. They don't have to. So for example, let's just take a look at, let's do this. CH3, CH3. So if I have cis-1,3 dimethyl cyclohexane and trans 1,3 dimethyl cyclohexane, so I have cis and trans, these are diastereomers. They are non-superimposable. They won't match up. If I try to get this part of the molecule to match up with that part, these methyl groups don't. But they're also not mirror images. If I drew an imaginary line here to represent my mirror, one is not a reflection of the other. Now, the other example is compounds with more than one chiral carbon. And as an example, we could have, and I'm going to use the Fisher projections here. That's why I wanted to get you guys Fisher projections first. All right, so let's do CH3, CH3, H, Br, and Br, and H, like so. All right, I can go ahead. This is 2,3-dibromobutane. I can go ahead and make, I'm going to call that sigma. It's a lowercase Greek letter sigma, and that represents a mirror plane or a plane of symmetry. It's not inside the molecule, but I'm reflecting across the mirror plane to make my mirror image. And these would be enantiomers. And so, just as an example here, I've made these two models, and you can see that one is a mirror image of the other, but yet they don't line up. If I try to get the black and green to line up, that works, but then the red and blue do not. No matter how I turn and manipulate this, they're not going to line up. So these are enantiomers, non-superimposable, don't line up, mirror image isomers. Now what if I did this instead? What if I drew the following? Okay, so now essentially what I've done is I've created this molecule here. It's not a mirror image of either of this pair of enantiomers, but it's not superimposable. Okay, I can get my blacks and my reds to line up. Sorry, my blacks and my greens to line up. I've got the reds and blues lined up here, but not up here. I could try to flip it around. Now I got the reds and blues lined up there, but not down here. So these guys are not mirror images, and they are not superimposable, so they are diastereomers. A diastereomer of the other two. So again, when we're talking about things like enantiomers and diastereomers, we're going to talk about pairs. These two are enantiomers. These two are diastereomers. These two are also diastereomers. Now, the example that I gave is actually a special case, and it's a case of what we call a meso compound. Meso meaning middle. So one thing that you might notice is that this compound has an internal plane of symmetry. If I took my imaginary plane here, or maybe it's a real plane, I don't know, and cut this in half, unfortunately, here, let me get my ruler, that's a little better. Here's my imaginary plane, my ruler. Cut it in half. The top is a reflection of the bottom. So that is an internal plane of symmetry, which means that this is not optically active. And we call this a meso compound. Okay, meso meaning middle. So we've got one enantiomer, the other enantiomer, and in the middle, quote unquote, is the meso compound. Now all of these carbons are still chiral. Each of these carbons is chiral. This carbon has four different things: hydrogen, methyl, bromine, and this other stuff. This hydrogen has four things, or sorry, this carbon has four things: hydrogen, methyl, bromine, and other stuff. We could even figure out the R and S configuration if we wanted to. So I just wanted to show you an example of diastereomers, also an example where Fisher projections are useful, and then talk a little bit about meso compounds. Now that is not to say that all diastereomers are meso compounds. They are not. Let's look at a different example. So I'm going to take a sugar here, a simple sugar. And draw its reflection here. And these guys are enantiomers. All right, now there's no internal plane of symmetry here because I've got an aldehyde up here and the alcohol down there. This is different than I've got this guy like this, okay? In fact, I could just rotate this whole thing. If I tried to make the mirror image of it, I could rotate it 180 degrees and get the same thing. You're allowed to do that with Fisher projections. I didn't mention, although you'll learn this in the lab, you can't rotate a Fisher projection 90 degrees. So let me just write that here. Helpful hint. It's okay to rotate a Fisher projection 180 degrees. And then I'll just add here rotating a Fisher projection 90 degrees makes the enantiomer. That only works if you have one chiral carbon. All right, so I've made my enantiomers here. Now let's make, and again, it's not a meso compound. So let's make another pair of enantiomers. So I'll do that, and then I'll do that. So comparing these two, I've changed the configuration at the bottom carbon. And now I can make the mirror image. So OH, H, OH. So these guys are enantiomers. But if I compare one of these two to one of those two, we have diastereomers. So these two are diastereomers, these two are diastereomers, these two are diastereomers, these two are diastereomers. Notice also that when we have two chiral carbons, we have a possible 4 different stereoisomers. So in general, N chiral carbons gives 2 to the N stereoisomers. Okay, there will be, if you start with one, you'll get the enantiomer, and then all the others will be diastereomers. Okay, so let me see what else I was going to say here. We can go ahead and, if I can find my, here we go, find my Fisher projection notes here. We can, if we want to, use the Fisher projection to get R and S. So here is this Fisher projection, and I happen to have my H is going in the background already, so that's good. So now I can just go around, from highest to lowest, so clockwise. So this would be R. Now, if I have, instead I have my H on the side, I have to flip it. Okay, I can do, so 1, 2, 3 should be, it's counterclockwise, so that would be S, but my H is in front, so it's actually R. It's kind of a shortcut you can take. You know, you could do the Kahn-Ingold pre-log system and orient your hydrogen in the front, and then whatever you figure out, just change the designation at the end. So if you have the hydrogen in front and you do the RNS designation and you get R, it actually is S. Okay, and I can show you some examples of that in person. I think it's a little easier to explain. But anyway, so I can take a look here and say that in in this example, I've got, let's see, carbon, so oxygen would be highest, carbon, carbon, those are tied, double bond to oxygen, single bond to oxygen, and a carbon. So this is second, so 1, 2, 3. So that 1, 2, 3 would be R, but since the hydrogen's in front, that's S. Let me write it in red here. Sorry, S. And then this guy is 1, well, that carbon and that carbon. This carbon is bonded to an oxygen. That's bonded to an oxygen. This carbon is bonded to 2 hydrogens. That one's a hydrogen and a carbon. So this has priority. So 1, 2, 3. So, is that right? 1, 2, 3. So that would be R, which would be S. Hold on a sec. Let me just double check this. Yes, that is also S. And if I have the enantiomer, I actually just switch the configuration at both carbons. Okay, so I have, instead of SS, I have R, R. All right, now here I've got, it's essentially the same sort of, the same thing basically. 1, 2, 3, R, so it's actually S, that would be R, R, and S. Okay, and I can do that here. Let's go back here and take a look. So this carbon, that's my highest priority. Between those two carbons, well, this one's attached to a carbon and a bromine. This just has hydrogen, so this is my second. So 1, 2, 3, like that would be S, but it's R because it's a Fisher projection with hydrogen in the front. And this guy would be 1, 2, 3, like that, which should be S, but instead it's R. And again, that's SS. Here we have R and S. So in this case, we have R, well, actually we would call this, if we wanted to label these guys, this would be 2R, 3R, 2, 3 dibromobutane. And this would be 2S, 3S. And this guy here would be 2R, 3S. Or 2S, 3R. Sometimes we would just call it meso. Okay, so if you're going to actually name the things that have more than one stereocenter, you need to indicate the R or S configuration at that particular stereocenter. All right, so we've got diastereomers, so non-superimposable, non-mirror image isomers. Sometimes, if we've got compounds with more than one chiral carbon, one of the diastereomers we get may be a meso compound. And these meso compounds have an internal plane of symmetry, and they are not optically active. Now, of course, we can have plenty of diastereomers that are not meso compounds. Another thing I do want to point out is that diastereomers will have different physical and chemical properties. Remember previously I mentioned that enantiomers will have identical physical and chemical properties except for when the compounds interacting with something that is chiral. Well, in this case, it doesn't matter. The diastereomers will have different physical and chemical properties. So they could have different melting points. They could crystallize differently. They could have different pKa values if they are acids. An example of that is tartaric acid. Okay. Let's see here. Yeah, I think that's about all I want to say. I've gone on for about 20 minutes, so I think that's enough for now about diastereomers and meso compounds. In the next lecture video, I want to summarize and draw a big flow chart for isomers, and then you guys should go ahead and practice identifying isomers. Work on the practice problems, and both the practice problem set and the end of chapter problems. All right, until next time, stay safe out there. Bye now.